Have you ever witnessed the miracle of life unfolding right before your eyes? The tiny crack in an eggshell, the determined pecking, and finally, the emergence of a fluffy new chick? It's an amazing process. But what if you don't have a broody hen? What if you could create that nurturing environment yourself? Welcome! Today, we're embarking on an exciting DIY project. We'll show you how to transform a simple, everyday fruit storage bowl into a fully functional, automatic egg incubator. We'll guide you step by step through the construction, from basic materials to wiring the electronics. And the best part? We'll use this very incubator to hatch our own batch of chicks. Our journey begins, like many great omelets, at the store. But instead of breakfast, we're looking for potential. We need fertilized eggs, the kind you can often find specifically labeled at local marts or farms. Let's grab a carton. Back in the workshop, these aren't just eggs, they're tiny vessels of life waiting for the right conditions. Our incubator's main body will be this clear, round fruit storage bowl. You might even have one like it at home. First things first, let's clear out the fruit. This sturdy plastic container provides excellent visibility and is easy to clean, perfect for our needs. We need both the base and the lid. The lid will house our control panel and heating element later on. Let's take some quick measurements to get the dimensions right for our internal components. Accuracy here will help ensure everything fits snugly later. Now for a crucial part, the egg tray. This needs to securely hold the eggs and allow for turning. We'll start by creating a base structure. Using a circle cutter, we'll make a disc from this white foam board or similar lightweight material. We need to know the size of our chicken eggs, so a quick measurement with calipers is helpful. Based on this, we'll mark out evenly spaced, egg-shaped positions on the disc. This incubator is designed to hold 12 eggs. To give the tray some structure, we'll cut a strip of the material, form it into a ring, and secure it. This ring acts as a wall. Now, we attach the marked disc to this ring, creating the lower part of our tray. We also need to drill some holes, smaller ones around the center for humidity circulation from the water we'll add later, and a central hole for the turning mechanism pivot. Next, we create the top layer of the egg tray. For precision, we're using a laser cutter on this gray acrylic sheet, but you could achieve this with careful manual cutting too. The laser cuts out the oval shapes perfectly sized for the eggs, ensuring they sit securely, along with the necessary central mounting holes and smaller humidity vents. To allow the tray to rotate smoothly, we're attaching a small plastic cup, like a sauce container, upside down in the center. This acts as a low-friction pivot point. A simple drawer knob is added to the top, which will serve as our manual turning handle and connect to the automatic turner. We place the gray top tray onto the white base structure. Let's do a quick test. Marking an egg helps visualize the rotation. By gently turning the top knob, you can see how the eggs shift position within their holders. This turning is vital to prevent the embryo from sticking to the shell membrane. Excellent! The completed egg tray assembly fits perfectly inside our fruit bowl base. While manual turning works, an automatic turner makes life much easier and ensures consistent rotation. Here's the heart of our auto turner, a geared DC motor. We mount it onto a metal bracket. Crucial for controlling the rotation are these microswitches. We'll mount 2 of them onto the bracket positions so that a lever arm attached to the motor shaft will activate them at the limits of its rotation. This tells the motor when to stop and reverse direction. We need to fine-tune the position of the lever and switches to get the desired turning angle. Roughly 45 degrees each way is ideal for chicken eggs. Small adjustments are made by loosening and retightening the screws. Now for some basic wiring. We'll solder diodes across the terminals of the microswitches. This helps manage the electrical flow for reversing the motor's direction. Wires are then soldered connecting the switches to each other and to the motor terminals. We use heat shrink tubing to insulate the connections safely. Using temporary alligator clips connected to a power source, we can test the mechanism. Watch as the lever arm moves, hits one switch, reverses, moves the other way, hits the second switch, and reverses again. Perfect automatic back and forth motion. With the turning mechanism ready, let's build the control panel which will sit on the incubator lid. These are the main electronic components we'll use. A digital temperature controller to maintain the precise heat needed. A digital timer module specifically for controlling the egg turning intervals. Momentary push-button switches for lights and manual turning override. A relay socket and relay, which will handle switching the power to the heating element. Again, we are using a laser cutter for a clean finish on this black acrylic sheet, creating an octagonal mounting plate with cutouts for our components and mounting holes. The channel name Imaginative Guy is also etched on. Using the finished plate as a template, we mark the hole positions on the incubator's clear lid. We drill pilot holes, then use larger bits and potentially a rotary tool or file to carefully create the openings for the displays, switches, and mounting screws. Take your time here for a neat fit. The plate fits nicely onto the lid. To elevate the control plate slightly and provide mounting points, we'll fabricate some simple wooden dowel spacers. A small lathe makes quick work of shaping and drilling them, but simple dowels cut to length would also work. These are then attached to the underside of the black control plate. Now, we mount the electronic components onto the plate, the egg turning timer, the temperature controller, the light switch, the turning switch, and the relay socket. They are secured from behind with screws and nuts. On the lid itself, we install the DC power jack, tightening it with a wrench. The automatic turner motor assembly we built earlier is then mounted securely underneath the lid, ensuring the motor shaft protrudes through the central hole. This is where careful wiring is essential. We connect the power jack to the main components. Wires run from the temperature controller to the relay socket, which will control the heating element. The timer is wired to control the relay for the turning motor. The switches are wired in to control the lights and allow manual activation of the turner. We also connect the LED light strips. It's important to follow a wiring diagram carefully and ensure all connections are secure and properly insulated. We solder connections where needed and use terminal blocks for others. For heating, we're building a custom element. We're using a standard computer cooling fan, a metal ring, copper wire formed into rings, and a number of power resistors, specifically 2475 ohm, 2 watt resistors. The resistor leads are bent to form hooks. These resistors are then connected in parallel and soldered evenly around the smaller copper wire ring. This creates a circular heating element. Another copper ring is prepared. The 2 resistor rings are joined with short wires, and the excess leads are trimmed. Power wires are soldered to the element. This resistor assembly is carefully attached to the computer fan frame. We drill mounting holes in the fan housing. The completed heating and fan unit is then mounted onto the underside of the main control plate assembly, using the acrylic posts we made earlier. The power leads for the heating element are soldered to the relay controlled by the temperature module. The fan wires are also connected to the appropriate power terminals. The temperature sensor probe is carefully inserted and secured, positioning it near the eggs to get an accurate reading. A small metal bracket is attached to the side of the incubator bowl. This will interact with the turning mechanism lever to prevent the entire assembly from rotating. With the construction complete, it's time for the moment of truth. We plug in the 12-volt, 5-amp power adapter. The displays light up. We can test the internal light using its switch, and check the turning mechanism manually with its dedicated switch. The temperature controller shows the current reading and the set point, while the timer displays its settings. Let's configure the incubator. We set the target temperature to 37.5 degrees Celsius, the ideal for chicken eggs. Using the timer module, we set the automatic turning interval. It's programmed to turn the eggs for a short period every 60 minutes. Humidity is critical for hatching. We add some water to the bottom of the bowl. Now, we carefully place our fertilized eggs onto the gray tray, fitting them into their designated spots. The lid with the control unit is placed on top and secured. The incubator is ready. Incubation begins. Turning the eggs regularly, either manually or automatically like with our setup, is essential. To check development, we can perform candling. Using a bright light source, even a smartphone flashlight works. We illuminate the egg in a dark room. On day 3, you might just see a small network of blood vessels starting to form. By day 8, the embryo is much more defined, looking like a dark spot with a prominent vascular system. You might even see movement. Fast forward to day 13, the chick fills more of the egg, and the air cell at the large end becomes more distinct. By day 19, the chick occupies most of the space, preparing for the final stage. Around day 18 or 19, it's important to stop the egg turning. This allows the chick to position itself correctly for hatching. We'll disable the automatic turner now. And then, typically around day 21, the magic happens. Time-lapse shows cracking, the first pip appears, a small hole pecked through the shell by the chick using its egg tooth. Slowly, painstakingly, the chick works its way around, cracking the shell. Look at that! Our first chick is emerging. It's often exhausted after the effort. We can offer a little gentle help removing shell fragments if needed, but it's usually best to let them hatch on their own strength. Welcome to the world, little one. Soon, others follow, breaking free from their shells. They huddle together for warmth under the incubator's light. Once the chicks have hatched and dried off, usually after about 24 hours in the incubator, they can be moved to a brooder area. Look at this successful batch. Our DIY fruit bowl incubator worked perfectly. For their first meal, we need something easy to digest. We're finely chopping some canned sweet corn and fresh greens. Small insects like mealworms, also chopped, can be added for extra protein. Here you go, little ones. Their instincts kick in quickly as they start pecking at the food. As they grow a little stronger, they can explore a safe outdoor space. They love pecking at the ground, chasing bugs, and finding fresh greens. It's incredible to watch them develop their natural behaviors. This little chick is already quite brave. Ah, the thrill of the hunt! Even a small worm provides great excitement and enrichment. They quickly learn to associate people with food and safety, often following close behind. Access to fresh, clean water is just as important as food. And there you have it. From a simple fruit bowl and some readily available components, we've built a successful automatic egg incubator and hatched a beautiful brood of chicks. It's a rewarding project that brings the wonder of new life right into your home. Thanks for joining us on this journey with the imaginative guy. If you enjoyed this project, give us a thumbs up, and don't forget to subscribe for more creative DIY ideas. See you next time.